Welcome to a code report solution video. In this video, we're going to be going over the solution to problem 4 from LeetCode contest 72 entitled kth smallest prime fraction. So the problem states a sorted list A contains 1 plus some number of primes. Then for every p less than q in the list, we consider the fraction p over q. And the question asks, what is the kth smallest fraction considered? Return your answer as an array of ints where the 0th index is equal to p, the numerator, and the first index is equal to q, the denominator. And note that your array A will have a length between 2 and 2000. The elements of A will be between 1 and 30,000, and k will be between 1 and the length of your array times the length of your array plus 1 divided by 2. So let's take a look at an example. In this example, our array A has the elements 1, 4, 5, and 7, and it's asking us to find the 4th smallest prime fraction. So something that's important to note about this problem is that because the integers that you're given in your array are prime, we know that all the fractions that you can create from these integers are also going to be sort of prime fractions, meaning that they'll be unique. So we don't need to worry about two different fractions created from two different elements reducing to the same 4, i.e., 1 over 2 and 2 over 4 having the same value. So all of our fractions will be unique, so we can use a priority queue and initialize it to be equal to each of the elements over the largest element in our array, which we know because it's sorted will just be the last element. And then while k is greater than 1, we will pop off the top element in our priority queue, modify it slightly, and push it back in, and continue to do this. And then once k equals 1, we know that the top element in our priority queue will be equal to our answer. So let's see how this works. So we start with our priority queue, which will, as a parameter, template parameter, take a user-defined struct called fraction, which we'll see when we get to our code. But essentially, that's just going to store the value of our fraction as a double, and then the indices of the numerator and denominator. So for the first element here, it's going to be 1 over 7 as a double, and then the indices 0 and 3. And so because k is equal to 4, we're going to pop this value off, and we're going to look at the indices and then decrement the denominator by 1. And what this will do is it will generate the next smallest fraction using the same numerator. So if we have 1 over 7, it's going to decrement the 3 to 2, and then that will refer us to 5, and then we'll get 1 over 5. So then we're going to push the 1 over 5 into our priority queue, and because we've set up our priority queues such that the smallest fractions will be at the top, 1 over 5 is going to get pushed to the front or the top. And because k is still greater than 1, we're going to pop this off. Once again, decrement the denominator index, so 2 will go to 1. This will then give us 1 over 4. We'll push that fraction into our priority queue. K is still greater than 1, so we'll push off 1 over 4 again. The denominator index will go from 1 to 0. This will give us 1 over 1, which will get pushed onto the back because it is the same value as 7 over 7. And at this point, k is equal to 1, so we know that the top element in our priority queue is equal to our kth smallest fraction. So 4 over 7 will be our answer. So let's take a look at the code. So at the top here, we have our user-defined struct called fraction, which has 3 members, our double value, which is just the value of our fraction, and the indices of the numerator and the denominator. So I is for the numerator, and j is for the denominator. And we have our constructor here, and our less than operator set up such that the smallest fraction will always be at the top of our priority queue, which is just based on our value. So we come into our function, kth smallest prime fraction. We set up our priority queue, taking fraction as its template parameter. We then set up our priority queue such that the initial fractions in our priority queue are equal to each of the elements over the largest element in our array, which, like we said before, because we know it's sorted, will be just the last element. So we can get that by using a.back. And note that we are using a cast here so that we're not going to be doing integer division. You could just use a C-style cast, but it's best practice to use explicit C++ casts, those either being static cast, const cast, etc. And then we set our indices. So I will be set to our index of our loop, and a size -1 will be constant for the last element. Then we come down to our while loop while k is greater than 1. We get our top element, then pop that off, decrement the denominator, which is j, and then we push on a new fraction by making a call to the constructor by doing something similarly that we did up here, but using the modified denominator, and then we decrement k. And if we continue to do this, we'll end up with our top value of our priority queue being equal to our answer. So we can just create our vector by using braced initialization and referring to the elements of our array A by using the numerator index I and the denominator index j. And finally, the complexity of this algorithm is going to be n log n, more specifically k log n, because we at most will be doing k pushes into our priority queue, and each push is going to be log n complexity. As always, if you enjoyed this video, hit that like button. Make sure to follow me on Twitter for reminders 30 minutes before contests start. You can find all of the code that I use in my videos on my GitHub page. All of the links are in the description down below. And finally, if you want to make sure you don't miss any of my upcoming videos, make sure to hit that subscribe button. Thanks for watching, and I'll see you in the next video.